Imagine you're an SRE, a site reliability engineer, and you get that alert, the one you dread. Latency has just spiked on your main platform.
Mm-hmm.
So you pull up a log for just a single user request. Let's say it's a universal search query, one that has to blend results from the web, from images, news, ads, everything.
Right.
Now, in today's world, that single request, it doesn't just hit one server. It explodes. It goes out across potentially thousands of machines.
Machines running software built by totally different teams, maybe even in different programming languages, and they're spread across multiple data centers.
All over the globe.
It's the ultimate needle in a haystack scenario,
Yeah.
except the haystack is, constantly shifting and the needle is only visible for a fraction of a second.
So you're looking at your big system metrics, and there's a problem somewhere.
But you have absolutely no idea where in that huge, intricate web of dependencies the fault actually lies. I mean, from the user's browser all the way down to the deepest, darkest storage systems. The engineer is, for all intents and purposes, blind.
Trying to debug a whole city with the tools you'd use to fix a single house.
Exactly. And that right there is the genesis story of Google's Dapper, their distributed tracing infrastructure. It was born out of, just stark necessity.
As Google scaled past the point where any single person could understand the whole system.
Right, where no single engineer could possibly map out every interaction. They needed something built into the foundation, an invisible, ubiquitous architecture to give them that intelligence.
And we're not just talking about debugging here, are we? This is more like providing a unified causal map of what happens when a request just travels across the planet.
And what makes Dapper such a masterclass in systems design is that they refuse to compromise on the non-functional requirements. They knew that if the tracing system itself caused problems, people would just
Turn it off.
They'd abandon it. So when you look at the original technical notes, they set up these 3 core design goals, 3 commandments, if you will, that were absolutely non-negotiable.
Okay, let's get into those 3 pillars, because I feel like everything else they built flows from these decisions. What was the first, and I guess the most critical constraint?
The first, and maybe the hardest to pull off at Google's scale, was low overhead. It just had to have a negligible performance impact.
Negligible.
I mean, we're not just talking about CPU or memory, we're talking latency. If running Dapper added even a tiny measurable delay to a core service, deployment teams would be incentivized to just disable it.
And if they disable it, the whole system loses that ubiquity you mentioned. It becomes useless.
Precisely. It's the classic paradox of monitoring. The measuring instrument can't interfere with the measurement.
Okay, so that's pillar number 1. What was the second goal?
The second was application-level transparency. The developers, the people actually writing the business logic, they shouldn't have to be constantly, manually instrumenting their code.
Yeah, that would never work.
No. If your tracing system relies on thousands of engineers remembering to add logging calls, it's going to fail. It becomes fragile, inconsistent, and ultimately you get an incomplete picture of the system. Dapper needed to be baked right into the foundational libraries, just running silently in the background.
So it had to feel totally invisible to the application developer. What about the third goal? I imagine it has to do with the sheer amount of data?
Oh, absolutely. That's scalability and pervasiveness. Dapper had to handle Google's massive size and, continue to scale robustly for years to come.
And we're talking about what kind of data volumes?
We are talking about generating terabytes of data every single day. And, crucially, making that data available for analysis extremely fast.
How fast?
The goal was to have trace data ready to be queried within a minute of it being generated, not hours, minutes. And that requirement, you see, it profoundly influenced all their storage and collection pipeline decisions.
So our deep dive today is really a journey into how they squared that circle, how they achieved that transparency and scalability while keeping the overhead practically at 0.
And they did it. They managed it through some incredibly clever data modeling, very specific architectural choices about how they collected the data, and honestly, some truly ingenious algorithms, especially around sampling.
Okay, so to really get why Dapper had to be invented, we need to internalize the problem size. Let's go back to that universal search example that the source material uses. Can you just kind of visualize the journey of one single web search query for us?
Absolutely. So the moment you hit enter, that query hits a front-end server. That server immediately becomes a coordinator.
And it's not just calling one backend.
No, it fans out. It distributes that query to hundreds of search servers, each one responsible for a tiny slice of the massive web index. These are all parallel calls, and they're all performance critical.
But the universal part is where the complexity just explodes.
Right.
It's not just about the 10 blue links anymore.
Correct. At the exact same time, that coordinator is sending requests to all of these specialized middle-tier services. You need spelling correction, you need an ad matching system, you need image search, news search, and so on.
And each of those can fan out again.
Now you're getting it. Each of those middle-tier services might, in turn, become its own coordinator and fan out to its own back-end databases or file systems. It's a dependency graph that just grows vertically and horizontally at the same time.
So we're talking about a dependency tree that could involve, conservatively, thousands of individual machines and services.
For one single user action, yes.
Wow.
And the really painful consequence of this fan-out architecture is that users are incredibly sensitive to latency caused by any single one of those subsystems.
The slowest link in the chain.
It's always the critical path. If the main web search comes back in 50 milliseconds, but the ad service or the image service takes 200 milliseconds, the overall latency for you, the user, is governed by that slowest component. If one process built by one team has a momentary hiccup, the entire system pays the price.
That sounds like a complete nightmare to debug, especially because the engineer debugging, let's say, Service A, has no built-in visibility into the performance of Service Z, which is 3 layers deep in the call stack.
Exactly. The engineer is facing these massive blind spots. They don't have a global view of the control flow. They don't even know for sure which services were involved because that list can be dynamic.
And they probably don't have the expertise to know why Service Z is slow.
Worse than that, that delay might not even be Service Z's fault. It might be Service Z just waiting for a shared resource, like a big table instance, which is currently getting hammered by a completely unrelated bulk data transfer job run by some other team.
This complexity really hammers home that first requirement we talked about, ubiquity. If you only trace 90% of the system, you can bet that your critical bottleneck is going to be hiding in that untraced 10%.
Oh, for sure. The sources stress that the monitoring has to be continuous and ubiquitous. You can't just turn it on when there's an outage. Because the very nature of these weird system behaviors, the one-off network lags, the brief moments of resource contention, it makes them impossible to reproduce in a lab. If you aren't tracing 24/7, you lose your one chance to capture the data when the anomaly actually happens.
So how do we actually track a single user request's lineage across this exploding dependency graph? This gets us to the fundamental difference in tracing methodologies.
Right. Historically, tracing falls into two main camps. You've got your black box schemes and your annotation-based schemes.
Okay, let's start with the black box approach. What does that look like?
So black box schemes, you see them a lot in academic research like Project 5. They're typically very lightweight and non-intrusive. They don't require any application changes.
That sounds good.
It does. But instead, they rely on having access to huge volumes of message records, things like network logs. They use statistical techniques, mostly regression analysis, to try and guess which messages belong to the same original request.
Guess. So there's a downside.
The downside is accuracy and data overhead. Because they're inferring causality, not asserting it, they need just massive amounts of data to get to a decent confidence level. They're inherently less accurate. And when the system topology gets really complex, the inference can just break down. You get fragmented or, totally misinterpreted traces.
So Dapper took the other path, the annotation-based scheme. This one relies on explicitly tagging every single record with a global identifier.
Yeah, annotation-based tracing is precise. If the ID is on the message, you know for a fact that the causal relationship is real. But traditionally, this meant heavy manual instrumentation. You'd need developers putting start trace and end trace calls all over their code.
Which immediately violates that transparency goal we talked about.
Immediately. So Dapper was stuck in this engineering dilemma. They needed the precision of annotation, but the transparency of a black box system.
How do they get out of that bind?
They leveraged the homogeneity of the Google platform. This is the really elegant part of the whole design. While Google's application landscape is huge, thousands of services, the underlying infrastructure is incredibly standardized.
Everyone's using the same basic building blocks.
Almost everyone. They're using the same core threading model, the same shared control flow libraries for asynchronous stuff, and crucially, a single standardized remote procedure call system, RPC, for all their inter-service communication.
So instead of instrumenting every application,
they instrumented the pipes and the wires beneath the application. They restricted their deep, high-fidelity instrumentation to that tiny, common set of foundational libraries. So the application developer doesn't have to think about Dapper at all. It just activates whenever they make a standard RPC call or schedule a callback or start a new thread.
They turn the biggest disadvantage of annotation, all that manual work, into an advantage by confining it to libraries that everyone was already using. Okay, let's pivot now to the specific architecture that makes all of this possible. If Dapper is modeling the entire flow of a request, it needs a precise language for it. And this starts with their core data model, the trace, which is modeled as a tree of spans.
Right. The entire unit of work, everything that happens for that one user request, that's the trace.
The whole tree.
The whole tree. And that trace is then broken down into its parts, which are the spans. A span is just the basic unit of work. It could be an entire RPC call, or it could be a localized function execution inside one process. It acts like a little log of timestamped records, capturing the start and end times, RPC data, and any annotations.
So if service A calls service C, the work A does before the call, the RPC call itself, and the work C does to handle it. Those are all distinct spans that form a nested part of the tree.
They are, and the crucial task is being able to reconstruct that tree after the data has been collected from thousands of different machines.
And that reconstruction, I'm guessing, depends entirely on some kind of unique identifiers.
It relies completely on 3 critical 64-bit probabilistic unique identifiers. These are the lifeblood of Dapper's causality tracing.
Okay, can you break down the purpose of each of those 3 IDs for us?
Sure. First, you have the trace ID. This is the common identifier. It's shared by every single span associated with the entire request, no matter which machine or process creates it. It's the global key.
The master passport for the entire journey.
That's a great way to put it. When a request first hits the front end, the root span is created, a unique 64-bit trace ID is generated, and that ID propagates everywhere that request goes.
Okay, that's number 1.
Second, you have the span ID. This is unique to that one specific unit of work, that one node in the tree. It just identifies the local operation in its own context.
And the third ID must be the link, the thing that defines the relationships.
That's the one, the parent ID. Every span, unless it's the absolute root of the tree, contains a parent ID, and that links it back to the immediately preceding causal span. So these 3 numbers, trace ID, span ID, and parent ID, are what allow the system to follow these incredibly complex asynchronous control paths and then stitch the entire timeline back together.
It's important to remember the physical reality here. The source material points out that the most common type of span actually holds data from 2 different machines.
Right.
The client that made the call and the server that handled it.
Right.
And that immediately brings up a huge technical headache. Clock skew.
Oh, it's a massive problem. When you have 2 different physical machines, their clocks are just never perfectly synchronized. You might have a client that records receiving a response at time t, and the server records sending that same response at time t plus 10 milliseconds, even though the actual network transit time was maybe 2 milliseconds.
So if you just naively subtract the timestamps to figure out how long the server took to process, your calculations are complete garbage.
Complete garbage. So Dapper can't rely on perfect time synchronization.
So how do they handle that inevitable clock drift and still give you meaningful timing data?
They apply a really clever constraint algorithm that's based on a fundamental principle, causality. Regardless of what the clocks say, some events have to happen before others.
The laws of physics.
Basically. The client making a request must occur before the server receives that request, and the server sending a response must occur before the client receives it.
So they use those immutable laws to put a boundary around the potential error.
Exactly. For every span that crosses 2 hosts, Dapper sets up a measurable set of lower and upper bounds for the server-side timestamps, all relative to the client's clock. The algorithm makes sure that the calculated server processing time respects these causality constraints.
So it doesn't solve the problem perfectly, but it constrains it.
It constrains it. It allows Dapper's analysis tools to calculate meaningful durations, even if the absolute timestamps disagree. It's a very pragmatic solution to a problem that just can't be perfectly solved in a distributed environment.
This complexity really shows why Dapper couldn't just rely on timing data alone. It needed context from the developers, which is where application-level annotations come in.
Yes. The instrumentation gives you the skeleton, right? The structure of the calls. The annotations provide the flesh, the critical context.
So what does that look like in practice?
Well, developers can use simple APIs, something like a trace printf, to just drop in timestamped text annotations. For instance, logging the result of a database query. Cache miss for user profile ID 1234. Little breadcrumbs.
And what about the key value annotations? How are those different?
Key value annotations are more structured, and they're really critical for processing later. They let developers maintain internal counters or log specific binary messages or pass contextual metadata around within a requests process.
Can you give an example?
A classic one is tagging any big table operation with the specific table name being accessed. This isn't just debug text for a human, this is structured metadata that allows later tools to do things like automated dependency mapping.
And this brings up a really crucial defense mechanism they built in, the limit on annotation volume. Why do they have to put a cap on how much a developer could log in a single span?
It was a system stability thing. Developers are creative. If they start logging entire debug streams or stack traces into the annotations, two bad things happen.
Okay.
First, they dramatically increase the size of the span data, which puts a huge strain on the collection system. But second, and more importantly, they risk displacing the core structural information that Dapper relies on, the RPC timing data and the causal IDs.
So the limit is there to protect the integrity of the trace itself.
It ensures that no matter how chatty the application logging gets, the fundamental structure of the trace is always preserved.
That attention to detail really extends into the collection pipeline. Let's walk through the 3 stages of getting the data from the application all the way to the analysis tools.
It's a pipeline that's designed for minimal intrusion and maximum efficiency.
Okay, stage 1.
Stage 1, logging. This happens right at the source. The instrumented application binaries, the things running the core Google services, they write the span data to local disk log files.
And the key here is that this is done asynchronously, right?
Absolutely crucial. The application doesn't wait for the disk I/O. It just hands the data off quickly to minimize any delay in its own foreground work.
Okay, so now the data is just sitting on the local disks of thousands and thousands of machines. What's next?
Stage 2, collection. This is handled by the Dapper daemon. It's a small, highly optimized process that runs on every single production host at Google. Its only job is to read or pull that data from the local log files and ship it upstream.
And the design of this daemon is a testament to that low overhead goal.
It really is. It uses less than 0.3% of one CPU core, even at peak load. And it operates at the lowest possible kernel priority. It's designed to be the ultimate background citizen, to make sure it never steals resources from a production service.
So the daemon gathers all this data from across the fleet. Where does this massive fire hose of data all end up?
Stage 3, storage. All the collected data flows into a centralized repository built on Bigtable, which is Google's massive distributed key value store. This choice was critical for scalability and for fast indexed access.
And the way they store it is a bit counterintuitive for a traditional database, isn't it? A single trace gets a whole Bigtable row.
It does. It might seem strange, but it brilliantly leverages Bigtable's unique properties, specifically its sparse table support.
Explain that.
Bigtable lets a single row have thousands of columns, and it's optimized so that columns that don't exist don't take up any space. So they use the trace ID as the row key. Then each column within that row corresponds to a specific span ID.
So since traces have a huge variance in length, some have 10 spans, some have 10,000, this sparse layout is perfect.
It's ideal for handling this highly unstructured data inside a structured key value store. It means that fetching the entire trace, no matter how big, is just a single fast lookup operation using the trace ID.
But we know the speed of this collection is impressive.
The median latency from the moment the application generates the data to the moment it's available in Bigtable is under 15 seconds.
Wow.
Yeah, that ensures the data is fresh enough for real-time debugging, easily meeting that design goal of being available within a minute.
Okay, before we move on, we have to talk about one of the most critical design choices they made. Out-of-band collection. Why did they decide to collect all this trace data separately instead of, say, just embedding it in the RPC response payload and sending it back up the chain?
That was a vital decision, and it came down to 2 reasons, both about preserving the accuracy of the measurements.
Okay, what's the first one?
That the first is just the raw size difference. We kind of touched on it earlier. If you have an RPC that fans out into hundreds of spans, the trace data you generate could easily be 50 or 100 kilobytes, maybe more. But the actual application payload, the search result or whatever, might only be 5 kilobytes.
So if you sent the trace data in band, the network payload would be 90% monitoring data and only 10% application data.
Exactly. And that would artificially inflate the network latency and completely bias any later network performance analysis. Your monitoring system would look like it was causing this huge network strain, when in reality, the application's payload was tiny.
So out-of-band collection ensures you're analyzing the performance of the application, not the monitoring tool.
Right. And what was the second reason? It's related to execution flow.
It's about the non-nested execution patterns you see in modern middleware. A lot simpler tracing systems assume this perfect synchronous nesting. A calls B, B finishes, B returns to A, then A continues.
Right, simple model.
An in-band collection relies on that. You wait for the nested trace data to flow back up the call stack. But in the real world, systems just don't work that way.
How so?
Well, a middleware service might kick off a back-end operation, get the main result it needs, and immediately return that result to its client, all while the back-end system is still doing asynchronous work, like cleanup or data replication.
So the RPC response has already been sent, the channel backup, the call stack is closed.
Exactly. An in-band system would lose the ability to trace all that subsequent async work. But out-of-band collection, with its local logging and the daemon, it handles those messy real-world flows seamlessly.
That makes perfect sense.
So we've established that Dapper's success really hinges on transparency. The developer shouldn't have to manually change their code. Let's look a little closer at the mechanism they used to achieve that and maintain causality through this minimal instrumentation.
Right. As we discussed, they focused on just 3 key points where control context can be transferred within Google's standardized infrastructure. And the genius is that these 3 points, when you put them together, are enough to capture the entire causal graph.
Okay, so the first one is the easiest. Threading.
Threading, yeah, this one's simple. When a service starts handling a request, the trace context, the trace span, and parent IDs gets attached to that thread using thread local storage.
So any function running on that thread just automatically inherits the IDs.
It does. It allows all the local work to be correctly timed and associated with the right trace.
Okay, the second one is much trickier. Asynchronous control flow. This is where you leave that linear path and defer work to, like, a thread pool or a callback.
This is where the causal link can so easily be broken. And this required them to instrument the control flow libraries themselves.
How does that work?
So if a developer schedules a callback function, the tracing system makes sure that the trace context of the creator thread is correctly bundled up and stored with that callback object.
Ah, I see.
Then later, when some worker thread finally picks up that callback and executes it, the context is restored. And that allows the trace to just seamlessly follow that nonlinear path. And this is critical because asynchronous operations are everywhere in high-performance web systems.
And the third point is the real glue, isn't it? The RPC framework. This is where the causal link has to jump from one machine to another.
Exactly. Since the RPC system is standardized, they instrumented it to do 2 vital things. First, to define the precise start and end of the RPC span on the client side.
And second,
To make sure that the trace ID and the current span ID, which becomes the parent ID on the server, are automatically transmitted in the RPC header.
so when the server gets the call, the instrumented framework on that side just automatically extracts those IDs and starts a new server-side span, creating that parent-child link with no manual coding at all.
That's the magic. It's just built in.
It's pretty amazing that under 1,000 lines of core C++ code could achieve this level of system-wide visibility. But let's get back to the cost problem. We can't forget that initial finding. Tracing everything came with a huge penalty.
A huge one. That 1-to-1 frequency tracing every single request increased average latency by 16.3% in their core web search cluster.
That's a system killer.
It is. It proved definitively that full rate tracing was commercially and operationally just not feasible. It makes the user experience worse, which makes the monitoring tool counterproductive.
So sampling became an absolute necessity. But how do you sample and not miss the critical information?
Well, the initial data showed that they could drop the sampling rate way down to 1 in 16, or even as low as 1 in 1024, which is less than 0.1% for the really high volume services, and the performance penalty just disappeared into the noise.
And the logic there is,
The logic is, if a service is getting thousands of requests per second, even a 2.1% sample rate is still capturing several traces every single second. If there's a consistent performance problem, it's going to show up reliably in those samples.
but there's an obvious downside to that kind of uniform probability-based sampling. What about the low-traffic services?
Exactly. If a service only gets, say, 10 requests an hour, and you're sampling at 1 in 1024, you might not capture a single trace for weeks. even though that service could easily afford to be traced 100% of the time.
And that's the precise challenge that led to their first big algorithmic innovation, adaptive sampling.
Right. Uniform sampling fails because it treats every service the same. It results in either a ton of data overhead for high-traffic services or just massive undercoverage for the low-traffic ones.
So how does adaptive sampling fix this? What's the key change in how you configure it?
Instead of configuring it with a static probability, like sample 1%, adaptive sampling is configured by a desired rate of sampled traces per unit of time.
Okay, so administrator doesn't say sample 1%, they say.
They say, I need 10 sampled traces per second from this service.
That seems like a subtle change, but the implications for automation must be huge.
They're massive. If a service is extremely high traffic, the algorithm automatically calculates a really low probability, say 1 in 50,000, to make sure it hits that target of 10 traces per second.
But for a low traffic service.
For a very low traffic service, the algorithm calculates a high probability, maybe 1 in 1 or 100%, to ensure it still hits its target rate. It just automatically tunes itself.
So the algorithm keeps the overhead consistent across the whole fleet while maximizing the useful coverage for the services that really need it. It's a self-tuning system.
Exactly. It achieves two key goals. It keeps the overhead of tracing predictable, which makes that low overhead goal viable, and it makes sure that even niche or rarely used services generate enough trace data to be useful for debugging.
And when a choice is kept, the system records the probability that was used to get it.
That's right, which allows later analysis tools to correctly reconstruct accurate metrics based on that known probability.
So that handles the runtime performance overhead. But the Dapper team had a second scaling problem further down the pipe. Managing the just huge volume of data being written to this central repository.
Right, which necessitated a second layer of control. Secondary collection sampling.
What was the motivation for this?
It was purely operational and administrative. I mean, even with adaptive sampling, Google was generating over a terabyte of sampled trace data per day. They just needed a throttle valve to manage storage costs and, critically, to make sure they didn't overwhelm the right throughput limits of Bigtable during peak times.
And this sampling doesn't happen at the application runtime. It happens later in the collection pipeline.
Precisely. It happens in the Dapper collection system itself after the data has been logged locally on the machines, but before it gets written to Bigtable. And the mechanism is algorithmic, but it's incredibly simple to administer.
How does it work?
For every trace the collector gets, it hashes the 64-bit trace ID to generate a pseudo-random number, Z, between 0 and 1. Then the administrator just sets a single system-wide collection sampling coefficient, let's say 0.5.
And if the number is below 0.5, you keep it. If it's above, you drop it.
That's it. If Z is below the coefficient, the entire trace is kept and written to Bigtable. If it's above, the entire trace is discarded.
The critical constraint here, which makes it different from the adaptive sampling, is that the decision is based only on the trace ID.
That constraint is paramount. It ensures that Dapper maintains what they call trace completeness. They never keep individual spans in isolation. You either get the full 1,000-span tree for a given trace ID, or you discard all of it.
Which must make data analysis so much simpler. You don't have to worry about fragments.
Immensely simpler. And the administrative benefit is flexibility and speed.
How so?
Well, adjusting the runtime adaptive sampling rate means pushing new configs out to maybe tens of thousands of application binaries. That takes time, and it has some operational risk. But the secondary collection coefficient, that can be changed instantly and globally by just adjusting one parameter in the collection system's config.
So administrators can immediately throttle the data volume hitting Bigtable if they need to because of cost or system load.
In real time.
Okay, so Dapper is this colossal success because it collects and stores incredibly complex data incredibly fast. But that data is only valuable if you can get to it and analyze it. And that brings us to the Dapper Depot API, or DAPI.
The DAPI is the programming interface that exposes all that raw Bigtable data. Google understood that the tracing team couldn't possibly anticipate every analysis tool that every other engineering team would ever need. So they just focused on providing clean access to the fundamental records.
Letting the wider engineering community build their own custom tools on top.
That was the idea.
And the sources say there were three main ways developers needed to access this data. The first one is the obvious one.
Access by trace ID. Super simple. An engineer sees a slow request in a log file. They have the 64-bit trace ID. They can use that for a direct Bigtable row lookup and get the entire trace back in one shot.
But for systems analysis, you often need to look across, billions of traces over time.
And that's bulk access. For large-scale bash analysis, the DAPI just leverages MapReduce. A user can specify a time window and a service, and the MapReduce framework just iterates over all the relevant bigtable rows, running the user's custom processing function on every trace it finds.
So engineers can run system-wide checks like counting error codes or analyzing serialization formats across the entire fleet.
Exactly.
And the third way, indexed access, sounds like it was the most challenging to design. Because the trace IDs are just random numbers. They don't give you any inherent structure for querying.
It was a huge challenge. If a developer wants to ask, show me all the slow traces from the ads service on HostX between 2 p.m. and 3 p.m., you can't scan the entire Bigtable repository. You need an efficient index.
But the index itself costs money and storage.
A lot of it. They found that the storage cost of a high-fidelity index was significant, only about 26% less than the trace data itself. So they experimented with different index types, and they realized that engineers most often combined their query parameters.
So what was the final optimized index design they settled on?
They settled on a composite index that balanced query efficiency against storage cost. It combined 3 features in this order: service name, host machine, and timestamp. This let them do quick lookups based on the parameters people used most often, letting developers zero in on problems without having to scan billions of unrelated traces.
Okay, let's move from architecture to impact. The sources give this fantastic example of Dapper's value right out of the gate, the optimization of the AdWords review service. This service saw latency improvements by 2 orders of magnitude.
The AdWords team used Dapper from its earliest prototype stages, and Dapper's traces just gave them this irrefutable visual evidence of inefficient execution.
What did they see?
The traces immediately highlighted instances of unnecessary serial execution on the critical path. Developers inheriting complex legacy code, they didn't realize they were issuing request A, waiting for it to fully complete, and then issuing request B when A and B could have been run in parallel the whole time.
And the visual trace graphs just made these hidden serial dependencies totally obvious.
It exposed all these assumptions built into the code that were just killing performance. It also exposed correctness issues, especially around database access.
Like what?
The trace data was crucial for finding cases where the service was needlessly sending read queries to the expensive, high-contention read-write database masters instead of the cheap, fast read-only replicas.
So that's not just a latency fix, that's a resource allocation fix that saves a ton of operational cost.
A huge amount. And the adoption wasn't painful for them either. They integrated it really easily.
How did they do that?
Well, to enrich the traces beyond just the RPC calls, they used aspect-oriented programming frameworks, like GEIS, and that let them just annotate key software components with an indicator like @traced. The framework then automatically wrapped those components with tracing logic.
So it reduced the effort even more for the application developers.
Exactly. Maximized adoption.
Another really critical case study was tackling long-tail latency in universal search. Because those outlier requests, the ones that take way too long, are what really drive users crazy.
Yeah, and when you have dozens of teams involved, everyone blames someone else. The search team blames the network team blames storage. Dapper provided the empirical facts that were needed to end all the finger-pointing.
What was the key discovery?
It came from analyzing the traces of the slowest requests, the ones with an end-to-end latency over 200 milliseconds. The analysis, which is visualized in one of the figures in the paper, was conclusive. Requests that had high outlier latency were far more likely to have encountered a momentary network degradation or increased network latency somewhere along their critical path.
So Dapper proved that while that network degradation might not affect the overall throughput or the median latency, it was the single biggest driver of those disastrous user-facing outliers.
It shifted the debugging focus instantly. It proved that optimizing network reliability and predictability, even in small ways, would yield massive dividends in cutting down that long tail, which is what users actually notice.
And beyond performance, Dapper really became a platform for system intelligence. Let's touch on the unexpected uses, like service dependency inference.
This is a direct result of those key value annotations we talked about earlier. Because developers were universally tagging bigtable operations with the specific table names, the DAPI's MapReduce tools could just ingest billions of traces and automatically build a real-time graph showing which services depend on which database resources.
Which is way more accurate and up-to-date than relying on some static config file or interviewing developers.
Far more accurate. And its use in security monitoring is fascinating.
Yeah, that seems like a great example of an unintended benefit.
It is. By instrumenting the code to log parameters of public security protocols, Dapper created this trace of security-relevant events, and teams use this to audit and verify that their applications were meeting internal security policies.
For example, checking that data being sent between services was using the right level of encryption.
Right. It offered this crucial layer of runtime assurance that a traditional static source code audit just can't provide.
So to round this out, we have to look at Dapper's limitations. After years in production, what did the system still struggle to fully address?
The first big limitation they identified was coalescing effects, which kind of relates back to that struggle with shared work. Dapper's model assumes a single trace follows a single causal path.
Okay, but in reality,
But imagine a disk subsystem that batches, say, 10 requests together for an efficient physical write. If only one of those 10 requests is currently being traced by Dapper, the system blames the entire buffered write time on that one single traced request.
giving it a deceptively huge time cost.
Right. And if 2 or 3 requests in that batch are traced, they all appear to share the same inflated span duration, which obscures the true individual latency. Dapper is accurately measuring the total time spent, but it struggles to correctly apportion the blame when work is deliberately shared and batched like that.
And so it struggles to disentangle the true cost of one request from the artifacts of shared resource efficiency.
Exactly. And that flows right into the deeper limitation, the challenge of distinguishing root cause from symptom. Dapper is peerless at showing you where the request spent its time, that's the symptom, but figuring out why that service was slow often remains ambiguous.
How so?
A service might be slow not because its own logic is expensive, but because it had to wait in a queue for 500 milliseconds. And that queue delay wasn't caused by the traced request itself. It was caused by an overload situation generated by thousands of other concurrent, untraced requests.
Since Dapper only traces the flow of its single request, it doesn't inherently see the external pressure. It doesn't see the queue lengths or the overall contention for a shared resource like a thread pool or a database lock.
Correct. Now, the sources do mention that developers can use custom annotations to log things like queue sizes, which helps mitigate this. But fundamentally, the single request tracing model faces this inherent boundary when it's trying to isolate causality in a shared multi-tenant system where resources are constantly being overloaded by external, unseen factors.
We've taken a really comprehensive look at Dapper today, Google's answer to the complexity crisis of distributed computing. And the accomplishment is clear. Dapper provides this deep, system-wide performance data using an architecture that is just incredibly minimalist and transparent.
And it achieved that primarily by instrumenting just those 3 common libraries, threading, control flow, and RPC, and then relying on those intelligent algorithms like adaptive sampling and secondary collection sampling to manage the massive scale without killing performance.
I think the most profound lesson, though, kind of transcends the technology itself. It's the decision to make Dapper not just an internal tool, but an open platform accessible via the DAPI.
Absolutely. By giving that raw data back to the engineers, Google managed to, and this is a quote, harness the creativity of a much larger community. And that led to this explosion of unexpected, valuable analytical tools, from automated resource accounting to verifying security policies, that the Dapper team themselves never could have built.
It turned data collection into a springboard for innovation. But the final takeaway is that even a system as advanced as Dapper still runs into the fundamental limits of observability when you're dealing with shared resources. Despite its incredible power, the blame game persists.
If the performance of your request is determined not by its own code, but by external pressure, a queue, a shared database lock, contention for a network path Dapper shows you where you waited, but it can't always tell you who caused the wait.
And that raises a really crucial question for anyone designing or operating complex infrastructure today. When resources are shared, can any monitoring tool that's built around a single request trace ever truly isolate causality without being able to see the pressure applied by the entire ecosystem?
What systems do you rely on where a hidden queue or a shared resource might be silently determining your performance fate?
That's something worth mulling over.
Food for thought indeed.
That was the deep dive on Dapper. We'll see you next time.